Precalc chapter 9, section 7. And so this is supposed to be 7 and 8, but we don't really teach 8 a whole lot more. We're going to stick with just 7, which actually splits us up. So we're going to ignore these last two, which is part 8. So we're going to look at polar graphing, how to graph polar equations. So to graph polar graphs, we can do one of three things to graph it. We can plot the polar points, and that's the method I'm going to go over in class. We can convert to rectangular linear graph, which isn't used a ton, or use parametric, which brings in our horizontal and vertical components of the polar graph. And so we're going to be using this method here, r equals f of theta. Parametric, to show you again, is we split it up into our x equals and our y equals in relation to their horizontal movement, cosine, and our sine movement, which is our vertical components of the parametric or the polar curve. So we're going to look at r equals f of theta, and so it's using our r, which is that directed distance from our pole to our point, and theta, which is our angle from the polar axis counterclockwise. And so if we're going to graph this equation, r equals 2 plus 4 sine theta, really all we're doing is plotting points. It goes back to when you first learned how to graph a rectangular equation. You just choose different theta values. So I would choose different theta values if I'm making a table, and then plug them in to find different r values. So we'll fill up this table. But to do that, I want to first realize we're going to evaluate sine of theta. So I'm going to choose theta values that make it easy for myself. So using the unit circle, I know the sine of 0. Sine of 0 is 0. Sine of pi 6 is a good one, because sine of pi 6 is 1/2. The sine of pi fourths and pi thirds uses the square root of 2 and square root of 3, so I'll kind of skip those. And I'll go right to sine of pi halves. So the sine of pi halves is 1. And then the next one, we know that's actually a whole number. It will be the sine of 5 pi 6, which is 1/2. I mean, keep going around the unit circle there and figure out ones we know. We know the sine at pi is 0. The sine at, let me extend my rectangle here. The sine at 7 pi 6. So I'm finding ones in the unit circle that we should know. So then we have the sine of 3 pi halves. And then the sine of 11 pi 6 would be the ones I'd want to write down. So 7 pi 6 is the negative 1/2. 3 pi halves is negative 1. 11 pi 6 is also negative 1/2. So these are the ones I'd look at in the table here, are different theta values. So I punch those in. The sine of 0 is 0. 0 times 4 is 0. 0 plus 2 would be 2. Pi 6, sine of pi 6 is 1/2. 1/2 times 4 is 2. 2 plus 2 is 4. So I put in sine of pi halves. I get 1. 1 times 4 is 4. 4 plus 2 is 6. Notice that this is the biggest value I can get. The sine of pi halves is 1. It's the biggest value I can get, which means that this is going to be my maximum value for r, my biggest possible r value. 5 pi 6 is 1/2. 1/2 times 4 is 2. 2 plus 2 is 4. And then pi is 0. We get 2 here. So I plot those points. So 0 is my angle. I go out 2 out. Now each of these rings represents 1. So 1, 2. And I could change that scale if I wanted to go by halves. At pi 6, so if I look at how this circle is broken up, here is pi 6, pi thirds. So this would be pi halves. So here's pi 6. So at 4. At pi halves, about 6. 5 pi 6 would be 4. And then pi is 2. So let's keep going then. If I keep going with this table here, so 7 pi 6. If I plunge in 7 pi 6, I get negative 1/2. Negative 1/2 times 4 is negative 2. Negative 2 plus 2 is 0. So I actually come back to the pole right here. 0. No distance away. 3 pi halves is negative 1, so if I do that, I get negative 2 here. So if I plot that, 3 pi halves is going downward here, but the negative 2 means I have 2 in the opposite direction. And then 11 pi 6, and then we get 0 again. So then we'll come back to 0 again. So we have to look at the order we plot these points to help me graph this. So I'm going to start here, I'm going to come up. The next point we plotted was over here, back down here to the pole, and then we're going to come back up to that inner point, back down, then back around. You have to realize when you graph these polar graphs, they're circular. You should be able to graph this in one continuous motion, kind of using a curved shape, and that helps me plot these. So there would be the graph. Now, when we're graphing this, we should see some symmetry here. And so that's what some of the notes here are talking about, is that polar graphs have symmetry. And so we can look at what kinds of symmetry there are. There is a line symmetry, line over theta equals pi halves, and that's one of the symmetries we have here. So if I draw my vertical line through pi halves, this would be symmetrical about that. The polar axis is not symmetrical here, but some of them would be. And then the pole means is it like rotational symmetry, different kinds of symmetry. And so there's a quick way to see some of them. If I know I have a function dealing with sine, so r equals f of sine theta. So sine theta is part of the polar graph, the main function. Then I know it's going to be symmetric with respect to the pi halves line. Pi equals pi halves. And then if I'm dealing with cosine, I know it's going to be with polar axis. It's going to be a symmetry. So those are quick ways to see what symmetry I'll be dealing with before I even start the problem. So let's do another one here. If I'm graphing this one, so I see it's cosine. So right away I should see symmetry over the polar axis, see some reflection over that. Now I could have more, but that's one of them I will have. Now when we graph these, we could use zeros and maxes to help. So the zeros occur for theta when r is 0. And then the max is when we have the biggest r value. That usually occurs when you have the biggest cosine or sine and you multiply it through the function. So we tend to use our calculator to help us graph a lot of these, and then we can use our previous knowledge to find points and create more points to help us out. For this one, we realize it's not just cosine theta, it's cosine 2 theta. That would change the problem a little bit. So when I'm thinking about what angles to choose for the problem, it's just not cosine. Like I know cosine of 0. So what does theta need to be to get that? 0. So I know cosine of 0 is 1. So the next one I know from the unit circle, that's going to give me an integer cosine of pi thirds. And that's going to give me a value of 1/2. Cosine of pi halves is 0. Cosine of 2 pi thirds is negative 1/2. Cosine of pi is negative 1. Cosine of 4 pi thirds is negative 1/2. Cosine of 3 pi halves is 0. And cosine of 5 pi thirds is 1/2. So these are the ones from the unit circle that we should be able to find that give us a nice number. And it's not an irrational number is what we are not looking for. So these are pretty easy to plot. These are the ones I tend to like to plot. Now we have to realize that we're not plotting cosine of theta, we're plotting cosine of 2 theta. So this has to be cosine of 2 times some number that equals the same angle. So this one here is going to be cosine of what number, 2 times what number is going to be pi thirds, and that's going to be pi 6. And then pi halves comes from cosine of 2 times pi fourths. Cosine of 2 times pi thirds would be 2 pi thirds. This would be the cosine of 2 times pi halves, which will give me the pi. So I'm trying to write it using the numbers on the unit circle times 2. So the ones on the unit circle, those are the ones I can graph quite quickly. So cosine of 2 times 2 pi thirds would be the 4 pi thirds. Would be cosine of 2 times 3 pi fourths. The last one here would be cosine of 2 times 5 pi 6. So these are our theta values that we're going to plug in here. The theta values we're actually going to plug in here are from this side. We can follow that. So I plug in 0 here, I'm actually going to be getting what's over here to become 1. And so then 1 times 4 would be 4. I have to finish up the equation up here though. Pi 6, I would get the 1/2 when I plug it in here. I get 1/2 times 4 is 2. For pi fourths, I'm going to get 0, and 0 times 4 would be 0. Pi thirds, it's going to be negative 1/2 times 4, negative 2. And pi halves, negative 1, which is negative 4. And so we can look at Pli's points. The 0 degrees, we're at 4 out. 1, 2, 3, 4. At pi 6, here we're at 2. At pi fourths, we're back at 0. At pi thirds, which is the line up here, we're at negative 2. So I'm going to come down and go negative 2 in the opposite direction. Then pi halves, we're opposite direction, negative 4. So 4 distance of 4. 1, 2, 3, 4 would be here. So if I just make a curve with these points, we're going to come up to this point, down, down around to this point. So that's the start of my curve. Then if I continue these points, and 2 pi thirds is negative 1/2, the cosine of 2 times 2 pi thirds is negative 1/2. Negative 1/2 times 4 would be negative 2. If I plug in the 3 pi fourths and plug it into this equation, I end up getting 0. And if I plug in 5 pi 6, I end up getting 2. So let's start plotting those. So 2 pi thirds, so that's over here, 2 pi thirds, I'm at negative 2. So that's down here at 2. 3 pi fourths, over here I'm back at 0. 5 pi 6, which is over here, I am at 2, so now I'm going to come back out. So if I connect those, continue from where I left off, I'm going to come up to this point, through the origin, and back around here. So you kind of see our circular patterns. And this actually continues. If I keep going with more of these values, this pattern is going to continue. I can use my symmetry. So instead of finding all these points, really the process is to use a calculator. The calculator will give me the shape, so I can kind of use that to help us find symmetry. And then after I know symmetry, and then our zeros and our maxes, I can plot this quickly. Because looking at the graph, I know I'm going to have a max here, I'm going to have max here, and then I have symmetry over both the pi halves and the polar axis. So I'm going to come down, back around here, up, around there, then back down, and then back around here. And so that would be the shape I got, kind of like a 4-leaf clover. And so the circular patterns, a continuous shape on how I'm drawing it, the use of our maximum and our zeros, the calculating the general shape, and then plotting some points using our trig would help us be able to graph these. So these general shapes, these are the ones you need to know the general shapes of. These circle, these are the different polar graphs we're going to be looking at by category. So here's a circle with radius 3. There's a cardioid. Think about cardioid reminds me a lot of a heart, so this looks a little like a heart, sideways heart. Look at the equation, it kind of comes from the setup. This is the limicon, or limicon, but that's when you have the circle within the other circle. And so you have the 1 plus 3 cosine t, an example of that. Notice the only difference here is here we have the even numbers, here we have the odd numbers. The pedal curve, so the pedal curve, this would be an odd pedal, but you can have even like the one we just did, and notice how the difference with 3 here, it doesn't match that number, like the last one we had was 2, but we had 4 pedals, but it's even odd would match here, but it's cosine. A pedal curve even, notice we have an even number here, it's like the one we just did. And then we have our ellipse, and notice we have some division sign here, the ellipse. And then the limescate, which is the infinity sign, kind of comes with these squares with the double angle, R squared, so you kind of see what that would look like here as well. So really you just need to know these by name. By name, can you identify the shape? I'm going to call that good for 9-7 on graphing polar graphs. Make sure you use your calculator, be able to plot points in polar mode, and make sure you use your symmetry and your max values to help you sketch the curves. We'll see you tomorrow.